Welcome to our first online lecture. We will continue with our optimization theory, and today we will be doing something called constraint optimization with inequality constraint. Let me briefly recap what we have done till now. We have studied a function f of x where this x is a vector, let's say d-dimensional vector. Okay, so it belongs to, we say, Rd, and our goal was to minimize f of x, and we had a subject to constraint, suppose g of x equals 0. So if you can see that this is an equality constraint, we have done several examples in the class also. Now, in addition to equality, there can be inequality constraint also. Suppose, for example, there can be inequality constraint that h of x is less than or equal to 0. I think we will do this with an example. It will become more easy. Let's suppose we have a problem of minimizing x1 square plus x2 square. Okay, and the constraint we have is one of the constraints we can have is, suppose that x1 square plus x2 square is less than or equal to, say, let's say some number 5. This is the inequality constraint. We can have equality constraint also, as suppose x1 plus 2x2 equals 4, and in addition to that we may put a condition that x1 as well as x2 should be non-negative. It should not be negative number, okay, greater than or equal to 0. Now, till now what you have done, if you have inequality constraint, suppose in the class, if you remember, we had suppose we had a maximize x1 plus 2x2 such that x1 square plus x2 square equals 1. What is the solution in that case? You have to first form a Lagrangian, okay, that is f of x plus lambda times the constraint g of x, right? And then you have to find the gradient and put that equal to 0. And what is gradient here? You can define it like this: the partial derivatives with respect to the three variables and equate that to 0. Now, in case of inequality constraint, as you can see here, x1 square plus x2 square is less than or equal to 5. What is the way out to do? This problem has been studied by three independent mathematicians. One is known as Karush, other mathematician as Kuhn, and the other as Tucker. These are three mathematicians. In fact, they studied this optimization problem separately and they provided a solution in their honor. This condition is called KKT condition, which we will state very soon. That is, if you have inequality constraint also, the solution was provided by these three mathematicians. And what is that solution? We will not do any proof, but we will just state it in a very simple terms. Okay, before that I have restated the optimization problem. So we have to minimize some function and let g now denote the inequality constraint. I will explain it with the help of example, and h denote the equality constraint. So in the context of our problem, we can see that g of x you can define as x1 square plus x2 square minus 5, and then this constraint is equivalent to g of x is less than or equal to 0, and equality constraint you can write as h of x equals x1 plus 2x2 minus 4, and hence you can write it as h of x equal to 0. You can see there are more constraints: x1 greater than or equal to 0, x2 greater than or equal to 0. You can define them like this. Suppose this you name as g1 of x, okay, this is g1 of x, and then you can define g2 of x as minus x1, g3 of x as minus x2. So what you can see, this you can also write as g2 of x less than or equal to 0, g3 of x less than or equal to 0. Okay, so now we will compare it with the standard form below. So it means we have minimization problem here, but the constraints can be simple. So I is equal to 1, 2, suppose up to m. And here also I can write it as j. So j is equal to 1, 2, up to m. We can have m constraints equality or m inequality constraints. Okay. Like in this example, in the above example, we can see that this you have three inequality constraints. G1 of x corresponding to this, G2 of x, G3 of x. So m is equal to 3. Sorry, we can. I want here. So j is equal to 1 to n. Okay, and you will see that we have only one equality constraint. So n is equal to 1. Let me first state the solution. Then we will do examples, and it will become very clear and easy. The solution provided by these three mathematicians is almost similar to what we have done with equality constraint. That is, first form the Lagrangian like this. F of x plus, if you have only one inequality constraint, write some lambda times, or say mu times g of x plus lambda times h of x. So why I'm reserving lambda, because lambda we have reserved for equality constraint previously also. So it means that whatever constraint is there, for every constraint, whether equality or inequality constraint, you have to introduce a Lagrange multiplier. Okay, Lagrange multiplier. Fine. Now since we have here many inequality constraints and possibly equality constraints also, suppose m inequality constraint and n equality constraint, so then we can index it like this. We can write here mu I gi and summation. So let me erase it. So we can write like this, because now we have m inequality constraint, so there will be m Lagrange multipliers for it. Okay, let me first state the conditions, then I will do the example. We say that the solution for this optimization problem is given by the following, something called KKT optimality conditions. What are those? Number one is the same, that is the gradient of this L is equal to 0. Number two, the inequality constant gi of x less than equal to 0, so I is equal to 1 to m. And number three will be, okay, of course before that this h j of x is equal to 0, equality constraint j is equal to 1 to n. And what is number? This is something which you have to write now, without proof, except the number three condition is, which is very important, that this product mu I gi of x should be equal to 0 for all I is equal to 1 to m. And along with that, these mu i's should be greater than equal to 0. If you recall, when we did optimization with equality constraint, I told you at that time that the Lagrange multiplier in case of equality constraint does not have any sign convention that it should be positive or negative. I told you at that time that when we will do inequality constraint, then we have to enforce a sign on mu I. The reason for that is beyond the scope of this course to show the proof. So these mu i's have to be non-negative. It cannot be negative. And yeah, these are the conditions. Sorry, there is no fourth condition. These are the three conditions. These are called KKT conditions. Now, till now, I can easily guess that you might be feeling very heavy, something very complicated. Of course, the proof is complicated. We will not do that. But let's now try to solve the above problem. Now note it down that whenever you have any optimization problem, this is the standard format. This is the standard form. Convert the problem into minimization and write the inequality constraints like this. Okay, so let's go to the problem and try to solve it. So here is the problem we were going to solve. Now let's see how we can write it into the standard form. So in standard form, basically you have f of x equals x1 square plus x2 square. Now you have inequality constraints, so g1 of x we can write as x1 square plus x2 square minus 5. Then you see you have x1 greater than equal to 2. But the standard form of optimization has this form, that the inequality should be of this form: gi of x less than equal to 0. But if you look at the inequality over here, it is x1 greater than equal to 0. To make it compatible, we'll define g2 of x as minus x1 and g3 of x as minus x2. So x1 greater than equal to 0 is same as g2 of x less than equal to 0, and x2 greater than equal to 0 is same as g3 of x less than equal to 0. And then we have equality constraint we denote by h of x, given x1 plus 2x2 minus 4. Now what is the solution? First form the Lagrange. So we'll form the Lagrange like this: f of x, which is x1 square plus x2 square, plus mu1 Lagrange multiplier for g1 of x, plus mu2 Lagrange multiplier corresponding to g2 of x, plus mu3 Lagrange multiplier for g3 of x, plus a lambda for equality constraint h of x. Okay, so now let's write it. Now here the mu1, we have g1 of x is minus x1, so it will be minus mu1 x1, similarly minus mu2 x2. Then I think the first constraint is mu1 x1 square plus x2 square minus 5 minus mu2 x1 minus mu3 x2. Okay, and then mu3, this lambda, times h of x, which is x1 plus 2x2 minus 4. This is the Lagrange. See, I repeat, for every constraint, whether equality or inequality constraint, you should have one Lagrange multiplier. Fine. Now the first condition, KKT condition for the solution, is that the gradient with respect to x1 x2 should be equal to 0. So del L upon del x1 is equal to, so this is differential of x1 square, which is 2x1. This differential of x2 square is 0. Then you have mu1 times x1 square, it becomes plus 2 mu1 x1, and then mu2 x2, its differential will become minus mu2. Then lambda x1, its differential will become lambda, and another one will become del L upon del x2. So we have x2 square, so differential 2x2. Then you have plus 2 mu1 x2. Then you have minus mu3, and you have plus 2 lambda, that is 2x2. You differentiated, the derivative is 2 and lambda is multiplied. So this we have to put equal to 0. See how many unknowns we have. We have unknown x1, we have unknown x2, we have lambda, we have mu1, we have mu2, we have mu3. 1, 2, 3, 4, 5, 6. We should have 6 equations. Now how will we get other equations? See, we need equality constraint to be satisfied, so that becomes your another equation, that is x1 plus 2x2 minus 4 equals 0. Then you have KKT conditions. You have this mu1 g1 of x equal to 0, that is mu1 times x1 square plus x2 square minus 5 equal to 0. Similarly, you have mu2 minus x1 equal to 0. Similarly, you have mu3 minus x2 equal to 0. Fine. And also you need a condition on mu1 should be greater than equal to 0, mu2 should be greater than equal to 0, and mu3 should be greater than equal to 0. Now look at this, how to solve it. First look at this equation and these two equations. So the first equation suggests us that either mu1 is 0 or x1 square plus x2 square minus 5 equals 0. Fine. So now you see one by one. If you put mu1 equal to 0, then it means that this cannot be equal to 0. Fine. And you can use this condition. So let's take case 1. let's take case 1 that mu1 equal to 0. Also you can take case that mu2 equal to 0, because this equation means either mu2 is 0 or x1 is 0. Fine. So let's assume mu2 is 0. So this equation suggests either mu3 is 0 or x2 is 0 and mu3 is 0. Let's say that this is satisfied. If you take this case 1 and then solve these two equations, what will we get? We get like this. We get these two equations. Why? See, case 1 is mu1 is 0, so this term is gone. Mu2 is 0, this term is gone. So this term is gone, this term is gone. So the two equations we have now to solve is this one. Fine. Along with the equality constraint that x1 plus 2x2 equals 4. So we have x1 equal to minus lambda by 2, x2 minus lambda. So this equation here becomes minus lambda by 2 minus 2 lambda is equal to 4, or minus 5 by 2 lambda is equal to 4, or lambda is minus 8 by 5. Fine. So for this lambda, what is now the value of x1? X1 is 4 by 5, 8 by 5. So 4 by 5 and 8 by 5 is one of the solution for this optimization problems. Okay, this optimization problem. And at this point, what is the optimal value? X1 square plus x2 square, which is 4 by 5 square plus 8 by 5 square, which is 16 by 5. This is the minimum value. Now in next class, what we will do is we'll solve the other cases when mu1 is not 0 but mu2 mu3 is 0, when mu2 is 0 mu3 mu1 is not 0, and we'll see what will be the other solutions for this KKT conditions. I will recap it in the next lecture. Don't worry, it may seem a little bit hard, but with examples it will be easier, and we will not do any complicated example for you. It will be kept very simple. And after the completion of KKT, I will have then a video session on how to implement this in Python. Thank you.